So for this last example, we're going to revisit the blood drive of collecting O negative donors, but this time I'm going to look at it in a much wider scale. So what if there is a nationwide blood drive that the Red Cross was conducting, and they wanted to collect 1,850 O negative units from 32,000 donors? So what are we looking at here? We have now increased our sample size, not at 20, but 32,000, and I'm referring to the previous video of 20. And we learned in the previous video that the probability of O negative donors is 6%. So the probability of O negative from the population did not change. All I'm doing is talking about collecting from a larger sample. And the question I'm looking at is they want to collect 1850. So what is the probability that X, being O negative donors, is equal to the 1,850? Now it's equal because if you look at the sentence, they haven't specified anything. They just want to collect 1850. They want to collect 1,850. So let's go to the calculator and in StatCrunch and see what this looks like. So we're going to change. First, we need to make sure we go back to the standard calculator, and I'm going to change my sample size to be 32,000. My probability of success for O negative doesn't change, but I am going to change the probability statement to be equal to the 1850 that I needed. So we're looking at what's the probability of getting 1,850 O negatives from a pool of 32,000. And you can see that the likelihood of that happening is 0.002. So not really likely to get the 1850. But what if I change the question here to say what's the probability of getting at least 1850? So now if we're thinking about at least, that says X, which are the O negative donors, are greater than or equal to the 1850 that I need, right? We need at least 1850. So I'm going to look for 1850 or more, which is why I chose greater than or equal to. So if I head back to my calculator, I'm going to change that inequality symbol to greater than or equal to, and you can see here that now it's a 95% chance of meeting the goal of getting at least the 1850 donors that I needed, so 0.952. So the likelihood or the probability of collecting 1,850 or more O negative donors from a pool, from a sample size of 32,000 happens about 95% of the time, which is good odds if you are working for the Red Cross and you're trying to set how many O negatives you need to have, right? That might be something of interest to you. Now, the last part of this question says, okay, well, how many O negative donors would we consider usual then in this case? So the term usual should bring back memories of the empirical rule. And if you remember, the empirical rule said that within 2 standard deviations of the mean, 95% of the data will happen. And then 5% of the time it falls outside of that. And so unusual is 5%. Usual in this case then would be 95%. So what we're being asked to do is to consider how many O negative donors do you think we can reach, the minimum number of donors and the maximum number of donors. So let's look at it this way. I know I'm going to use the empirical rule for this. And the empirical rule uses not only the mean, but the standard deviation. So let's calculate the mean of our O negative donors. For a sample size of 32,000 and a probability of getting O negative donors at 0.06, 32,000 times 0.06 is going to be equal to 1920. So we would expect out of 32,000 donors that on average about 1,920 of them would be O negative. Now, what's our standard deviation for that? Remember, the formula for standard deviation is going to be NP1 minus P. So here we have 32,000 times 0.06 times 1 minus 0.06. And when you put that into the calculator, you'll find, I'm going to round up to the nearest whole person, that that's 43. So before I go any further, if I want to use the empirical rule to apply the mean and the standard deviation, I have to have a distribution that's bell-shaped. And we saw that as soon as I went to 32,000, I definitely had a bell-shaped distribution. In fact, let's pull my calculator back up. You can clearly see that with a sample size as large as 32,000, this is a normal distribution, so I can apply that empirical rule. Now, the empirical rule said in the middle is our mean, and in this case was the 1,920 O negative donors out of the 32,000 we would be seeing. And to the left of the mean, I'm going to subtract 2 standard deviations, and to the right of the mean, I'm going to add 2 standard deviations. So when I subtract 2 times 43 from 1920, I get the 1836. So let me just write that down out here. So this is going to be 1920 minus 2 times 43. And then if I add 2 times 43 times the 1920, I end up with 2006. So again, that's 1920 plus 2 times 43. So what this means, according to the empirical rule, is that if I am within 2 standard deviations of the mean, this is what is usual to happen, right? 95% of the time, this 95% of the time, this is what will happen. So 95% of the time, out of 32,000 donors, I would expect anywhere between 1,836 O negative donors all the way up to 2,006 O negative donors. That's what happens 95% of the time, which is the number we're using to consider usual. Anything that happens outside of that would be considered unusual, right? Anything that happens outside of that is considered unusual. So if I want to talk about things that are considered usual versus unusual, I can use this empirical rule and add or subtract my 2 standard deviations from my mean, which we're calculating up here, to be able to answer that question. And this is an important question to be able to answer, because if you are, let's say, working for the Red Cross and you know that you can consistently, let's say, get 32,000 donors from a nationwide blood drive, then if you have a minimum number of O negative donors all the way up to a maximum number of O negative donors that you can expect to happen, then that tells you whether or not your goal of collecting some number is going to be achievable.